right? And how, if differential causality happens, somehow or other happens, what do we do? Let me share my screen. Okay, so we are talking about differential causality. So let's take some example. I will take one example. There is a cell, there is a capacitor. So is there any dynamics in this one?
No, it will achieve steady state like.
Yes. So it has no dynamics, absolutely no dynamics. So this has no dynamics. If you even start this capacitor with 0 hertz, the current will be infinite at t is equal to 0, and then onwards it will be 0. So it will take 0 time to charge this capacitor with a Dirac delta current. So let's model this. Source of paper. You put here 1 or 0, doesn't matter, because it's only 2 bonds. It will get removed. See, and the stiffness is 1 by C. So now, when you put its causality, you will directly get a differential causality. Source of paper causality comes here. Whether it is 1 junction or 0 junction doesn't matter. If it is 1 junction, you must have at least 1 causality away. If it is 0 junction, you can only have 1 causality near, others have to be away, so it is here. So this is differential causality. The answer is no. Okay, let's see from energy point. What is energy let final charge? Q. Okay, so what you have, E is equal to Q by C. So what is the energy stored in capacitor?
CV squared by 2.
Let's call it EC Q square by 2C. That is integration of step forward by C dq from 0 to Q. So that's the energy stored in the capacitor. Now let's see what is the energy given by the cell. That is E I dt, integral from 0 to infinity, whatever time. So we have basically E constant, dq 0 to Q. We can change that variable. So you have dq, which is Q by C, so Q square by C. So the cell gives energy Q square by C, capacitor stores half Q square by C. So half of the energy square by C given, Q square by 2C stored, half of supplied energy is lost. something seriously wrong. What is seriously wrong is that if you have a Dirac delta function at p is equal to 0, that Dirac delta function's integration actually has to begin from minus epsilon to plus epsilon with epsilon tending to 0. So the positive part after 0 becomes half. So anywhere you have Dirac delta function, that means okay, the model is essentially missing a time constant. So we don't have a time constant. Okay, charging takes place at 0 time. So this is what is revealed by the differential causality. So how to solve? So let us introduce time constant. These are missing dynamics. So what we have cell, some resistance, R. This might be internal resistance of capacitor. If you charge capacitor, you will see capacitor gets heated.
Sir, there seems to be a lot of lag. It might be better if you turn off the video.
Okay, fine. Introduce internal resistance of the cell as R. Or where or whatever. So in that case, our model gets modified to now have a 1 R C. This R is responsible for heat generation during charging. It is the internal resistance of the cell, it could be internal resistance of the capacitor, or everything combined, lumped together. So if you do that, then you will see our causality becomes correct, absolutely correct. You give here, cannot proceed, give here, then this. Okay, this R is in conductance causality. So as for this causality, its equation is F is equal to E by R. So R cannot be equal to 0. If R is 0, this is singular. Again, back to that differential causality thing. All right. So we can introduce a resistance. Okay, that is our missing dynamics. Then, whatever the value of this resistance, it will always dissipate half the energy. Whatever be the value. Whatever the value of R are not greater than 0. It dissipates half Q square by C. It doesn't matter what is the value. Basically, this will change the time constant of the system. So, if you plot somehow or other, let's say, let's plot here is energy dissipated by, let's say, resistance and time, you will find this is I square R, basically I square R, or let's say not energy, power versus time, power in resistance. So if resistance is small, your I square R is B square by R. This is B square by R, B is constant. So small resistance, this will be a high value. Large resistance, it will be a low value. Area remains same. It's constant. So the dissipation, whatever the value of R, you can put any straight resistance. Model will be fine. Give whatever value, doesn't matter. So it is important that when you see a differential causality, there can be some kind of energy inconsistency in the model, or there is a loss of time constant. That's the major thing. There is a loss of time constant. I can take another example. It seems a lot of people are interested in vehicles, so I will take this. Whatever we have done in class, let's say it is rotating at speed omega. There is a ground, and this is brought into contact with the ground for linear velocity initially. So what we have here R. So you have 1 omega. I is to J. This SC, I have put torque, it can be 0. It can be 0. Then you have transformer, radius R. Then we find slip. This is 1 linear velocity, which will have linear velocity finally, where you have masses to them. And here is our slip resistance, R friction at the ground. So here is slip. Flow is equal to slip. So let us assume pure rolling. Let us. If you assume pure rolling, then there is no dynamics. When the thing is accelerating, either the angular velocity is accelerating or linear velocity is accelerating or decelerating, then you cannot have pure rolling. So when you have pure rolling, everything is constant speed. Constant speed means no dynamics. So if we have, suppose pure rolling, then what should we have? The slip must be 0. Slip is equal to 0. Equal to 0, V is equal to omega R. And let T be 0. T is equal to 0 also. Then, if it is 0 this part, so equal to B minus omega R minus B, whatever you do, equal to 0. E may be whatever, E dot F is equal to 0. So this can be removed. No power. So this is removed. Alright? Once that is removed, we put causality.
Sir, R is a resistance due to friction.
Yes, yes. R is resistance due to friction. When you are pure rolling, then what do you have? What is the frictional force generated? Frictional force is 0. If you don't have any air resistance, let's say on this, then frictional force is 0. Because if you have frictional force, this acceleration, there will be linear acceleration. Alright? So if you apply 0 torque and rolling in some hypothetical case without any air resistance, then it has no linear acceleration, it has no angular acceleration. All right. If it has angular acceleration, then obviously you will have some kind of slip. All right. So if you have omega r is equal to v at all times, then slip is 0. It doesn't mean that force is 0. Okay. Force might be present. Force might be present. Right. But power in that is 0. Power, because there is no slip, so no power is 0, right? So once power is 0, that particular bond goes. Right. Zero junction stays because zero junction disappears only when effort becomes 0. If effort is 0, then this whole zero junction disappears. Okay? Right. So it's not that the frictional force is 0, it is that the slip is 0. Fine? So slip is 0, flow is 0. Now, in that case, if we give some causality, let's say this torque anyway is 0, but let's put it, it can be something. If torque is there, then for pure rolling, we must have some kind of external resistance here, air resistance or something. Have this. Once you do this, this is removed. This is removed. Okay. So this is here. I will not put causality. So this comes in. This is differential causality. What we can see here is originally the system had 2 degrees of freedom. If that friction there was slip, system has 2 degrees of freedom. If this resistance was present, then we can give this one also integral causality and change the causality of that. That RF is there, we can adjust the causality with RF. So if is present, not pure rolling, there are 2 DOFs. Number of DOFs is equal to number of I elements. This is very basic. The number of I elements in integral causality is number of DOFs. With zero slip, that is pure rolling, DOF is equal to 1. We have 1 DOF. Obviously, okay, omega r and v are coupled, so we cannot have 2 DOFs, but we have 2 I elements. So if we have 2 I elements, that means we have 2 degrees of freedom. But okay, when you put causality, we see one comes differential causality, so we have only 1 DOF. Okay. As per our causality, the degree of freedom is omega. If we had given this one integral causality, then that omega I appearing at omega will come in differential causality. So either V or omega, one of them you can choose as independent coordinate. Other one is dependent coordinate. So whatever is dependent, that comes under differential causality. So I can reduce this model now. This resistance is gone. This zero junction, we can remove it. So we will just reduce and rewrite that model. Reduced model. Transformer. Next was the zero junction, that's gone. Yeah. That is the thing we have. differential causality. Now I will show you, interestingly, this has one duet. This is one duet. This has no duet because this is derivative causality. So let's see some interesting thing here. A transformer, something here R connected to whatever 1 or 0, doesn't matter, I is some F. Let this be E1 F1, this is E2 F2. This can be removed, so this is not a problem. I put it E2 F2. Same, it's same. Whatever causality doesn't matter. So for this, we can always write F2 equal to R times F1. Then we have E2 is, let's write in differential causality form, mass times F2 by dt is mass F2 we put here, a mass times F1 by dt. Again for transformer, E1 is equal to R times E2. So E1 is equal to mr square times F1 by T. That's what it is. So we have directly E1 related to F1. So this one we can replace by E1 F1. I is equal to, they are related by a mass equivalent mass, a mass square. So that's basically coming to parallel axis theorem. Okay. So in this case, it's parallel axis theorem. You can have that same thing in hydraulic domain, in electrical domain, or whatsoever. Okay. There it's not parallel axis theorem. So when you have a transformer connected to some element, transformer connected to inertia, basically effective inertia becomes mr square. If you have transformer connected to a spring, suppose K, then equivalent stiffness becomes K times that transformer modulus square. That's it. And always it becomes get square. So if you do that, then our model reduces to, the further reduction is AC is to T 1, I is equal to J which is half mr square, assuming thin disk, and another I which is mr square. Two inertia, we can merge them. Two inertia having same velocity, same angular velocity. So we can merge them. 1 I is to P by 2 mass square. Basically, we have inertia about instantaneous center of rotation. Of center. Okay? Omega doesn't change. Moment doesn't change. Why? Omega and T do not change. Because there are three vectors. Remember first year mechanics, couple moment is a three vector. Likewise, rotation is a three vector. Alright, so if you translate those things, they do not change. But the inertia has got changed, and we have the inertia about the instantaneous center of rotation. Okay, about the contact point, of course, about the contact point when you put here. So then, once you reduce that DOF, we have a perfectly well causal model, no problem. So we have this, good enough. Here it was like this, this. This was bad, this was okay. So basically, okay, there was a loss of time constant, conversion of rotational motion to linear motion or linear motion to rotational motion has to take place in some time. If that time is missing, that time is coming through that frictional resistance. If that time is missing, then you cannot model those two things as separate degrees of freedom. You have to merge them and make them single degree of freedom. Otherwise, you have to include the resistance in the model. So most often we see that you can always get free if you are rolling, even with this model, by making this frictional resistance very high. If you make this frictional resistance tending to infinity, then what will happen? Whatever be this difference between these two forces, the slip will tend to zero. Will not be zero, it will tend to zero, and you will get pure rule. Alright? So it's always better to maintain this resistance in the model and vary its parameter. Likewise, in the previous case, you can get ideal, almost ideal voltage charging cell in zero time by setting this value of R very small, but not zero. Then it will be equivalent to directly cell connected to the capacitor. So these are singularities. These singularities arise because of differential causality. We need to remove them. So I will just discuss one thing and then I will leave. So to avoid, to remove differential causality, we can introduce parasitic elements. This is nothing to do with bond graph. This is common in modeling. Parasitic elements, that is small time constant. Which is also called implicit constant. There are explicit constants which we have modeled, whatever model we develop, and there are implicit constants which are actually not there, but we introduce them as extra things, and then somehow or other try to remove those through limits. So those are implicit constants. For example, let's say we have a mass, another mass, small m, big M, and they are connected by a spring damper. Simple thing like this. We have 1 I is to small m.
Sir,
Yes. Yes.
sir, so if there is differential causality, so can we say that this system is not having any dynamics?
A part of the system maybe, not the whole system. Other places there might be integral causality. Okay. That part of the system where differential causality is there, that will not have dynamics.
Okay.
For example, this one, we can say between M and M there is no dynamics. M and small m are same. Okay. But we can introduce a dynamics. We can introduce a dynamics and say that dynamics is negative afterwards. Okay. Then we will also have same thing.
Okay, sir.
Sir, in the
Yes. Tell.
previous case, there was a case of a differential causality and one integral causality, one with the J and one with the M.
One had a dynamics that one of them, rotation or the other thing. If you put torque, okay, the angular velocity, suppose it accelerates, with that the velocity of the wheel changes, linear velocity changes instantly. Okay. So
Sir, I was telling like one had integral and one had differential causality, right? So
yes,
when you are doing the transfer, when you are reducing the transformer, like using that MR square, so then you added the both terms. So how
yes,
can we add like when they have different
you
causalities?
you can add, no problem, as long as they have same velocity. So two masses having same velocity are one mass. Suppose these two masses, okay, they are there. Suppose they are unable to separate. You have glued them together here. Somehow other glued them. There is glue. Glue or weld or whatever. Then what is the total mass? M plus M. Okay. Because they are appearing at same place, but their velocity is same. So kinetic energy, if you write, it is half capital M x square plus half small m x square. So that is effectively one mass. Right? So that's how we got it. Yes. Yes, yes, also. Okay, okay, I'm trying to finish. Okay. So this is the case. So what